Good evening, everyone. I hope I'm audible and visible to all of you. Can anybody please confirm? Yeah, okay. Yeah, sure. Okay, so today will be the last session for the live sessions on fundamentals of electronic device fabrication. So before moving into the session, first we'll have a brief recap. So before moving into the brief recap, I hope all of you have gone through all the content for all 4 weeks and the entire course has been uploaded, and I hope you have already done and submitted your assignments as well. And roughly about in 1 month, you'll be having your final exam. So it's better that you finish these contents as early as possible. So in the last week, there were uploaded lectures on process evaluation, clean room, as well as IC packaging. So in that first we saw what is meant by process evaluation. We know that in IC fabrication there are multitudes of steps that is taking place, from wafer fabrication, patterning, then metallization, polishing, and so on. So the entire process will somewhat take for a particular IC in about a month. So if we wait for the process evaluation to be conducted at the end of the whole process, there is a possibility that the large number of dies that are manufactured could lose their functionality. Therefore, we will be including process evaluation steps at each of these processes at the end of each process, and this evaluation is carried out using different parameters that are known as yield. So different yields include wafer fabrication yield, wafer sort yield, and packaging yield. So it's important that you memorize what is meant by all three of these yields. So fabrication yield means the wafers that is out of a particular fabrication divided by the wafers that started in the fabrication. So, and each of these fabrication will be from a particular station, and the cumulative fabrication yield will be a product of the fabrication yield from all of the stations. Next comes the wafer sort yield. It refers to the, that is the functioning dies on the wafer divided by the total number of dies on the wafer. And finally comes the packaging yield, which means the packaging passing the final testing divided by the total number of dies that were started for packaging. And then we went on. So, as I mentioned, total fabrication yield means the fabrication yield from each station. And there are multiple factors that affect fabrication yield. That is the number of processing steps. As the number of processing steps increases, there is a possibility that the fabrication yield will decrease. Then comes wafer breakage and warping. That is, when we are handling these delicate wafers, there is a possibility that when they are moved from one station to another, there is a possibility of breakage. And when these wafers are subjected to a lot of heat treatment, there is a possibility of warping of the edges, etc. And then include process variation. Process variation refers to the specification limits. Each of the processes that is carried out in a specific station will have a range of acceptable values. Like in the previous week, we saw what is meant by the range of thickness values that could be accepted, range of resistivities, etc. This is included in process variation. Then we have process defects. This also affects the fabrication yield. Process defects means the defects that are introduced into these wafers by virtue of the processes that is happening, because of the operator, because of the equipment or the process, etc. Then we have what is known as mask defects. These are defects that are introduced in the wafer due to defects in the actual mask that were used for transferring the pattern. And then we went on to see what is meant by yield model. Yield model actually helps us in correlating the defect function density versus the yield. So there are different correlation functions. We have a Poisson's distribution, and then we have a Gaussian distribution, and Gaussian distribution in turn includes the uniform distribution, triangular model, and the seeds model. And if you have gone through the lectures of the past week, the equations related to each of these has already been discussed. I hope you have taken notes related to that, because today we will be having questions related to that. That is, depending upon the defect density in the wafer, we can predict the possibility of yield of a particular number of defects. That is what is given by these yield models. And then we went on to see what is meant by fabrication cost, what are the fixed costs, what are the variable costs, and how to calculate the overall cost, etc. And then next came the clean room design. That is, when we are dealing with these wafers, these are high precision processes, and it is necessary that contamination should be kept to a very minimum level. The reason is that we are actually handling equipments that are in the nanometer range. So even a human hair that is about 100 microns or a particle of dust will be more than the size of our chip. So it is necessary that the place where we carry out these operations would have a specific limitation on the maximum number of size of contaminants as well as the concentration of contaminants. The maximum size of the particles as well as their concentration are given by different Indian and international standards. So if it is something like ISO 5, it means that the maximum particulate size will be 10 power 5 per meter cube. So that is similar to the federal standard of class 100. So that is what is meant by clean room designations. And then we went on to see what are the different clean room designs. Currently used designs is known as what is meant by a ballroom design. Here we will be having the service stage, that is where we will be getting the assembling equipment as well as the maintenance equipment, etc. This is the actual region where the process equipments are loaded, and HEPA filters, that is, high efficiency particulate attenuators, will be used to pump out the contaminants from this particular regions and then again take them to the filters and provide a continuous supply of clean air. It is necessary that the entire region should be contamination free, especially from the commonly found contaminants like sodium, chlorine, and etc. So then we went on, then the highly sophisticated process tool designs are also used, where the wafer will be loaded and unloaded in specific chambers that are under environmental control. That is, the amount of contaminants will be very less in these particular regions. It will be under high vacuum, and the relative humidity, temperature, etc. will also be regulated. And this is a highly automated system where the wafers are loaded and unloaded using isolation pods. And then we went on to see what are the different circuit elements. We saw both active and passive circuit elements. Passive circuit elements include resistors, capacitors, and so on. So doped and undoped regions would act as resistors, and whenever we are inserting a dielectric layer, that would serve as a capacitor for charging. And then the active circuit elements. Active circuit elements are those elements that introduce energy into the systems. These usually include diodes and transistors and so on. And then we saw the manufacturing of silicon gate MOSFET. That is the entire processes that we have seen so far. That is the layering process, then how the mask was placed, then patterning operations, followed by metallization, polishing. The entire process was described for a silicon gate MOSFET. And then we went on to see what is meant by IC architecture or using logic states. That is, whenever we are using a chip or die, the functionality will be given in terms of an on or off state, that is a 0 or 1. And depending upon the type of the assembly of the transistors or diodes, we will be able to perform different logic operations like the OR operation, AND operation, NAND, NOR, NOT, etc. So we'll be seeing that through our questions. And now finally we went on to see what is meant by packaging and bonding. Once the die functionality has been assessed, each of these dies will be separated using scribers, and then will be fixed onto a packaging. And eventually from the packaging, leads will be given and electrical contacts will be bonded, and finally they will be sealed in a hermetic seal. So different types of bonding operations for establishing the electrical leads were seen. We saw about what is meant by ball bonding, where we will be using a capillary tube for inserting the electrical tube. Then we saw what is meant as a wedge bonding. Then came tape bonding. It is used for very thin wafers, where the leads will be given onto a very thin tape, and this process will be completed by what is meant as a thermode. A thermode will be a heated diamond tip that is then will be pressed onto the top of this tape for establishing the electrical contact. And then the further types of bonding include flip chip bonding. Here a solder will be used for establishing the electrical contact. Here separate step is not used for bonding. That is, the solder will be given onto one side of the package and the chip will be actually flipped onto the surface of this package. And finally, we have seen hermetic as well as non-hermetic seals for the final IC. So this is what was discussed in the last class, and actually the content for the last week are actually more than the previous week. So I suggest that you go through it, and it would initially be difficult to assess the content. So I suggest that you see it multiple times and understand. So now we will move on to the question answer session. I hope it is visible to all of you. Can anybody please confirm? Yeah. Oh, yeah. Okay, thank you so much. So now we'll move on. So based on the summary as well as whatever you have made notes for the last class, we will start our session. So first question is, the process in which electrical leads are deposited on a thin film and then stamped before bonding with the chip is called. So I have mentioned about wire bonding, wedge bonding, tape bonding, and flip chip bonding. So in which of these processes are the electrical leads actually deposited on the thin film and then stamped before bonding with the chip? So does anybody know the answer based on the notes you have made or your memory? Yeah. No, that's not the answer. In flip chip bonding, actually, we will be using solders, right? So here we are doing something known as stamping. So in which of these were we using a heated material to actually stamp the tape onto the surface of the wafer? So I hope now we have got the answer. It is not flip chip bonding. So you have three options left right now. Yeah, tape bonding is the right answer. So in tape bonding process, the electrical lead system will be first deposited onto a flexible tape, and this is done by sputtering or thermal evaporation. And after the electrical lead has been given onto the tape will be aligned with respect to the wafer, and we will be using something known as a thermode. Thermode is our heated diamond piece. That heated diamond piece will be then pressed onto the surface of the tape, thereby creating a bond between our wafer and the lead. So, in case of wire bonding is usually used when we are using gold, and wedge bonding is usually used when we are using aluminum. In both these cases, the wire will be fed through a capillary, and by thermomechanical compression, we will be bonding the die and the lead. And in flip chip bonding, as I already mentioned, these wires will not be used, and in place of wires, a solder will be used, a solder bump, that is a small drop of solder will be used, and then it is deposited on top of the lead, and the chip will be actually flipped onto the surface of the wafer. So that is what is done in flip chip bonding. So is that clear for all of you? The different types of bonding processes. Yeah, yeah. Yeah. In wedge bonding, aluminum is also used. The thing is that it should be having very high conductivity. That's all. Yeah. Yeah. In wire bonding also. And since we are using in nanometer dimension, it should be strong enough such that in the nanometer dimension, it should be stable. That's all. We can go for gold, aluminum, etc. That is possible. Yeah. Yeah. Okay. We hope that's all. And now we'll move to the next question. The fabrication goals, which we have to be met at individual process levels, are referred to as. So, in each of the station or the fabrication, we have a particular fabrication goal that has to be met. So, what is this goal called? Fabrication yield, process window, process yield, and wafer sort yield. Does anybody know the answer? So, while we are doing each of these process, so what is that we have to achieve from each of the process? No, fabrication yield, if you remember the definition, fabrication yield means the number of wafers out divided by the number of wafers in, right? So it is related to the wafer. And if we see wafer salt yield, it is actually the number of good dies out divided by the total number of dies in. So A and D won't be the answer. It is either process window or process yield. So what is the goal? That is, what is the thing that we have to achieve in each of the station? No, process yield is also not right. So it's actually process window. So process window means that the range of values that is acceptable, right? So whether we are measuring thickness or we are measuring the level of dopants or contaminants or whether we are measuring what do you say electrical resistivity etc. There will be a range of values that is acceptable, and these range of values is called as the process window. And this is our goal from a particular process. That is, whenever we are doing a fabrication step, we need to meet the process window. That is, the measured value should lie between these acceptable ranges. Is that clear? Yeah. Yeah. So, like if you can take a minute to read what is given in the box so that you get a better understanding. Process and device evaluation in the fabrication is used to make sure that the fabrication goals are met at individual process level. These goals are usually defined as a process window for each step in the fabrication process. So I hope that's clear for all of you. Now we'll move on to the next question. An individual step in an IC manufacturing process is called. So we have fabrication, automation station, and tooling. Yeah, station is the right answer. So when we are manufacturing an IC, there will be multiple steps, and each of these steps will be performed in a particular process, and the process will have specific instruments, etc. And this particular composition is known as a station. That is a region or a place using a specific set of equipments. We will be performing a particular step, a particular process. So that is what is meant by a station. Each individual step in an IC manufacturing process is called a station, and the wafers in fabrication go through a number of such stations to form the final IC. So I hope that's clear for all of you. Now we will move on to the next question. That is, a term used to describe a cluster of defects on a wafer is. This is actually discussed during the video. If you have gone through the video, it's mentioned. So whenever we have a wafer, instead of the wafer of the defects being randomly distributed throughout the wafer, usually the defects will be in one particular point or one particular location. It will be scattered in one similar region. So what is the term used to define this cluster of defects? No, defect density is actually the number of defects per unit volume, right? So defect density is not the answer. It is somewhat related to what? On a wafer, there's actually defect. This cluster of defects is an unwanted term, right? So there is a particular word for that. Yeah, decoration. Decoration is the right answer. Yeah. So a cluster of defects on a wafer is known as decoration. That's right. So now we'll move on. The yield model, which uses an exponential function for the defect density, is called. So as I already mentioned, we have different yield models. That is to relate our yield, that is the sorting yield, to the defect density, to the size parameters, etc. And for defining these, we have different mathematical models. There are multiple models like triangular model, Seals model, uniform model, Poisson's distribution, etc. So which of these models will use an exponential function for finding the defect density? Sorry? No, Poisson's model is not the answer. It's like exponential function. If you have noticed the graph, triangular model won't come, uniform distribution won't come because from the name itself we can predict the graph how it would be. So then it would, yeah, see its model as the answer. So let me take a minute and I will just show you the graphs once more. See here we have Poisson's distribution will be the density distribution will be distributed like this, whereas in uniform distribution it would be like this. And here we can see the seeds model is the one that actually follows an exponential function. Is that clear? Yeah. Okay, so now we'll move on to the next question. Okay. As the area of die on a wafer increases, which of the following statement holds true? So first you should understand there will be a large wafer and then on that wafer there will be small squares or functional units known as dies. So as the area, it is actually for a given wafer size, as the small squares or the dies become larger, which of the following statements hold true? Defect density remains the same, wafer diameter increases. Yeah, yeah, option C is the right answer. The wafer sort yield decreases. So I would like to explain it for people who didn't understand it. So see here we have three wafers. All these wafers, suppose don't see these values, just assume that all these three wafers are of the same size. So for the same size of wafer as the so suppose they have the same number of defects also. So here we can see most of the regions are yellow, which means that the yield is very less. That is for we have 10, there are total 28 dies and for 10 good dies we have 18 dies. 18 bad dies. Therefore, the yield will be very low. Suppose the die became smaller. See, the area of die on a wafer increases. That is, this is the largest case. Suppose the die became very small. Here we have much smaller squares, right? Even though there are 33 bad dies, we have 103 good dies. Therefore, the yield will be higher compared to the last case. And finally, when we have very tiny dies, suppose we have a total of 658, and out of that, approximately 38 are only bad, which means that the yield would again be higher. Therefore, we can see that as the size of the die increases, the wafer sort yield will decrease. Wafer sort yield means the good dies divided by bad dies, right? So the sort yield will decrease. So that is the explanation. I hope everybody understood. Does anybody require more clarity? Yeah. So you just look at these figures and you will be able to understand. Here the dies are very small. Here the dies are intermediate side. Here the dies are very large. So when there are large dies, the yield will actually decrease because for the given number of defects, total number will be less, right? So the wafer sort yield will decrease. So in order to understand questions like these, please memorize the definitions of wafer sort yield, fabrication yield, etc. So that's the case. So now we'll move on to our next question. Yeah. Yeah, sure, sure. No problem. So suppose here the question is, as the area of die on a wafer increases, which of the following statements holds true? First, we should understand that this whole circle, this big thing is known as the wafer. The small, small squares on it are known as dies. And here the area of die on a wafer is increasing. So here we have small dies, larger dies, very large dies. So here we have, suppose this this wafer has a large number of dies, that is 658 dies are there on this particular wafer. We have 38 bad ones and we have 620 good ones. So if we divide 620 divided by 658, we will get an yield that is approximately 94.2 percentage. But as the die size becomes larger and larger, even though the number of bad dies are approximately similar, what happens? Here the yield would be 103 by 136, which means that as the die size increases, the yield would start decreasing. And here when we have very large die, that is only very few small square, like big squares are possible on this wafer, our total yield will further decrease because only 28 are there, out of that 18 are bad. Here, since 620 are there, even if 38 are bad, the yield will still be good. So as the die area increases, the wafer sort yield will decrease. So is that clear? Yeah. Okay. So now we'll move on to the next question. That is, for process chemicals used in the IC industry, which of the statements will hold true? They should have a high concentration of sodium for better conductivity. They should be low sodium grade chemicals. They should have high amounts of chlorine. They should have high amounts of potassium. So in the IC industry, for different processes like polishing, metallization, etching, etc., different chemicals will be used. So which of the following statements is true for those chemicals? What kind of chemicals should be used? So it should have high concentration of sodium, low concentration of sodium, high amounts of chlorine, or low high amounts of potassium. Yeah, they should be low sodium grade chemicals. So can you try and giving the reason for why they should be low sodium grade chemical? Sir, it's actually related to the concentration. Suppose we have a wafer in the nanometer size and we use dopants. Dopants will be used in parts per million and parts per billion, right? So if they have additional metals present, that will give rise to ions. And these ions will be, suppose there is NaCl in your chemical, and they will dissociate it into Na plus and Cl minus. These Na ions will start contributing to your conductivity, right? So whatever doping you did will not be of use because dopants will be present in very small concentration and the functionality of the dye will be lost. So that is the reason. Is it clear? Yeah. Yeah. See, sodium is the most common mobile ionic contaminant. That is, it is capable of dissociating and it will function as a mobile ion. It will be capable of conduction. These MICs are electrically active impurities and can alter a semiconductor device performance. Therefore, we should be using low sodium grade chemicals because remember that dopants are always added in parts per million or parts per billion. And if we have additional metal ions present, they will contribute to the conductivity and as a result, functionality will be lost. So I hope that's clear and now we'll move on to the next question. A logical operation that gives an output of off when both inputs are on is called. So there are AND gates, OR gates, NAND gates, etc. Right? So which of these will give off when both inputs are on? Yeah, that is correct. So the gate that is used in our case will be a NAND gate. So the truth table, as you might have already learned for AND and OR gates, for a NAND gates, when both are off, what will be the output? It will be on. So suppose there is an easy way to remember NAND and OR. The only thing is that we have to think about AND gate and then calculate the opposite. That is, suppose we have off and off for an AND gate, it will be off, right? So here it would be the opposite. It would be on. And for example, if we have off and on for an AND gate, the output would be off, right? So in case of NAND, it would be on. So whenever there is an N present, just use the normal gate, that is AND or OR, and then negate it, that just put the opposite, that's all. So here this is the truth table for a NAND gate and NOR gate, and hence if we have both inputs on, what will be the output for a NAND gate? It will be an off. So is that clear? Yeah. So next we will move on to the question. Which of the following statements is false with regards to an IC manufacturing process? An undoped region in a wafer cannot access the resistor. In a metal oxide semiconductor based capacitor, metal can be replaced by heavily doped polysilicon. Many types of resistors can be patterned on a wafer. IC fabrication is an assembly line process. So one of these statements is wrong. Which statement among these is wrong? So if you have like a brief memory of whatever we have learned through the past 4 weeks, you will be able to identify. In an entire IC manufacturing process, one of these statements is wrong, which is that. No, many types of resistors can actually be patterned. Yeah, it's not the answer. Actually, it can be done. Yeah. So another option. So, like many types of resistor designs can be patterned on a wafer, right? So, first we need to think in a wafer what is meant by a resistor. Resistor actually means some region that gives us a change in the resistivity value, and this resistivity change is achieved by doping, right? So, now you can think on that line. Many types of resistors can be patterned on a wafer. Yeah. Yeah, that's correct. An undoped region in a wafer cannot act as a resistor is the wrong option. Why? In wafer fabrication, resistivity changes are achieved by changes in doping. So one region will be doped, one region will not be doped. That actually gives us a change in resistance. So A will be the answer. So now we'll see why the other options are true. So first case is false. Resistors are used for controlling the current flow. Every doped or undoped region in a wafer can act as a resistor. And actually dopant concentration would be used for controlling the resistance. And many types of resistor designs can be patterned on a wafer. So A and C is done with. And now we have B. In the metal oxide semiconductor based capacitor, the metal can be replaced by heavily doped polysilicon. That is true. A capacitor is a dielectric region that is sandwiched between electrodes. And the simplest dielectric structure that we have come across in the past 4 weeks is the MOS, that is the metal oxide semiconductor. And the contact in this particular case can be heavily doped polysilicon or any metal layer. We have already discussed that. So next is IC fabrication is an assembly line process. Yes, one after the other in a sequential manner, the wafer will move from station to station, and finally we will get the complete IC. So the integrated circuit manufacturing is similar to an assembly line manufacturing process. Wafers move from one station to the next. Starting point is the blank single crystal silicon wafer. Various processes are finally done to get the finished product at the end. So I hope the answer is clear to all of you. So just remember that any undoped region or doped region in a wafer is actually a resistor. That is the amount of doping will give rise to a change in the resistance. And therefore both doped and undoped region can act as a resistor. Is that clear? Yeah. Okay. So we'll move on to the next question. Choose the correct statement in case of a bipolar junction transistor. So those of you who have already seen the week's content, you will be able to know what is meant by BJT and what are the regions in a BJT. We all know that in a BJT there will be an emitter, base and a collector. And from which of the statement is true? Emitter is moderately doped region. Base is the heavily doped region. Base has the least width in the transistor. Emitter has a larger width than the base and the collector. It is a fairly direct question. Yeah. The base has the least width in the transistor. The answer is correct. So if you remember the structure of a BJT, we will be having an emitter, base and the collector. Emitter will be highly doped and it will have a moderate width, and the base will be the least doped and it will have the least width, and collector on the other hand will be the longest but it will be moderately doped. So this is actually the schematic for a bipolar junction transistor, and based on this we will be able to say that the base has the least width in the transistor. So I hope it's clear for all of you. It's a fairly direct question. Okay, so we'll move on to the next question then. Which of the following are both active circuit elements? So we have a set of options here: resistors and diodes, diodes and transistors, capacitors and diodes, resistors and capacitors. So which of the following are both active? Sorry, which one? Diodes. Yeah. The both of you are right. The correct answer is diodes and transistors. So now, can anybody give me what is the difference between active and passive circuit elements? Like what are their functionalities? Why are they called active elements, and so why are some called passive elements? Yeah, and what would be the passive elements? Yes, that is correct. So, to put it in precise words, I would say that diodes and transistors are the active elements which actually supply energy or introduce energy into the particular IC, whereas resistors or capacitors, as she already mentioned, are the helping elements. That is, they modify the introduced energy. So, that is the difference between active circuit elements and passive circuit elements. Is that clear for all of you? Yeah. So the next question is a logical operation that gives an output of off when either both or when either or both inputs are on is called. So you just take a sheet of paper and just write down that input 1, input 2. So our particular thing, we don't know which gate is that, but our gate will give an output of off. The answer will be off for both, when both will be either on or when one of them is on. So based on the table that I've already displayed, you will be able to answer this question. So you have to write input 1. Yeah, sorry? No, I please read the question. Like, we please focus once more on the question. See, our logical operation is that output is off when something is on. So it's definitely not and or. It's something like NAND or NOR. See, it's giving the ulta. Yeah, that is the correct answer. NOR is the correct answer. So I would like to show this particular thing again. See here, whenever you are given a question for a logic gate, please follow this habit of keeping a table. That is, you write input 1, input 2, and whatever output you want. So my question was, we wanted to get off in the output when both the inputs were on or when one of them were on. So in second, third, and fourth rows, we can see here that in these two cases, one of them is off on, and in the last case, both of them are on. And in all these cases, our output was off for a NOR output. That is what the question was. So I hope it's clear for all of you. So the question is the logical operations that gives an output of off when either or both inputs are on is called the NOR operator or NOR operator. Is that clear for all of you? Yeah. Okay. So next question is which of the following is the 4-bit binary representation for decimal 25? So, like how to represent, so here you have to be careful. It is a 4-bit representation. It is correct. So, can you please explain why it would be? Yeah. Option D is the correct answer. It cannot be represented using 4 bits. So, for that, we need to find out the maximum number that can be represented using 4 bits. Yeah, so that is the correct answer. So I'll tell you how we can do only from 0 to 15. So here it is given, it's a 4-bit representation, right? So whenever we have 4-bit or n number of bits, the maximum number that can be represented would be 0 to 2 and minus 1. Here our n will be 4, and when we substitute n, 0 to 2 power 4 minus 1. 2 power 4 is 16, right? So 0 to 16 minus 1. So only from 0 to 15 we will be able to represent using a 4-bit representation. If we want to represent 25, we will be requiring a 5 bits, right? Is that clear for all of you? Yeah, so that is the case. So I would like to for you to just find out for the next class or in the discussion forums. If you're not able to find out, please do ask in the discussion forum how to express numbers in the binary representation. So if somebody knows, you can either come up with the answer right now, or you can find out by yourself how to represent 25 in the binary representation. That is, how do we get this 111001? Does anybody know here? If that's not the case, then please do it like a homework assignment. Yeah. Somebody unmuted? Yeah. Yeah, that is correct. So I think many people might not have understood that. So please find it as a homework assignment how to represent 25 in the binary representation. How do we find this particular number? So in case you do not get the answer, please get back to me using the discussion forum or personal email, and I'll forward the answers to you. So now we'll move on to the next question. That is, a 10-step fabrication process has a cumulative yield of 0.85. Assume that 8 steps have the same station yield, while the other 2 steps have an yield of 0.93 and 0.98. What is the yield of the first 8 steps? So this is a problem that is actually taken from a previous assignment. So there is a possibility that such questions can come for your exams. So we have a 10-step fabrication process, and the overall yield will be the product of all the yields, that is yield 1 multiplied by yield 2 multiplied by yield 3 and so on up to multiplied by yield 10. So in that case, first 8 steps have the same yield, and the last 9th and 10th station values are given to you. So how would you find out the yield of the first 8 steps? So, can anybody start? Like, how would you start solving this particular problem? Suppose you take that for the first 8 steps, the yield will be x. How will you find the value of x? That is the question. Cumulative yield means it will be the product of yields. So, you have to multiply and find the value of x. How would you find the value of x? And remember that it is a 10-step process. And 2 are given, 8 are missing. So, then you need to find the value of x. Should I display the answer, or does anybody have any suggestions or way in which we can start this particular question? Okay, I think since nobody is responding, I would myself display the answers. Then, so cumulative yield represents the product of yields of the individual station. So suppose we are taking, as I mentioned, first 8 station has an X yield. So it is given that they have the same yield, right? First 8 stations have same yield. Therefore, we are taking it as X. And total yield is 0.85. Therefore, we will write 0.85 into x power 8 into 0.93 into 0.98. Here we are writing x power 8 because it will be like x1 into x2 into x3 into x4 into etc. up to x10. x9 and x10 are given here, and x1 till x7 is the same. Therefore, we will be taking it as x power 8. Is that clear for all of you? And finally, we'll get the value as 0.991. Yeah. So just remember that cumulative yield will always be a product. Out of that, a few steps will be given, and it will be usually that other steps have the same yield. Then we have to just take the product and find the value of x. So is that clear? And shall I move on to the next question? Yeah. Okay, so I'll move on to the next question. Which of the following represents fixed cost in IC fabrication? Equipment, chemicals, wafers, or reticles? It's a very direct question. Yeah. So the rest are variable costs. That is only when we are actually carrying out the IC fabrication, the other three will be used. Equipments are the fixed cost. Are those which are present regardless of whether the facility is used or not. Equipments used in fabrication represent fixed cost along with overhead costs like administration, facilities, research, circuit designs, and so on. Chemicals, wafers, and reticles, on the other hand, will be used only when we are actually starting the fabrication process. So with that, I'll move on to the next question. Changes in the wafer due to various thermal processes it's undergo during the IC manufacturing is referred to as, I've mentioned this during the summarizing part. So thermal treatment or heat treatment we are giving, then what happens to the wafer? Yeah, that's the correct answer. Wafer wrapping is the correct answer. So warping takes place when wafers are heated to and cooled from a high temperature, example being rapid thermal annealing process. So I hope it's clear for all of you. Now we'll move on to the next question. Which of the following chip characteristics affects or affect the packaging? Note that more than one answer may be correct. So in case in somebody who's not remembering what is meant by packaging, once we have the wafer and we have identified the functional dies, each of these small squares will be cut down using scribed lines and these small squares will be placed onto the package, and after they are placed onto the package it will be given electrical contacts or leads, and finally they will be packed. So if anybody who has opened their motherboard or any other who has worked in an electronic lab might be knowing, there will be small black colored chips or dies and they will be having multiple leads coming out of them, etc. So that is what is meant by a package. So which of these characteristics affects packaging? Lithography, dimensions, level of integration, and wafer thickness. So I would give you a clue. Three options are correct out of these. So just tell me which is the wrong option. Yeah, option A is wrong. So dimensions, level of integration, and wafer thickness actually affects the packaging. So just remember that lithography is basically the transfer of pattern onto the wafer or the die. It doesn't have anything to do with the actual packaging. So it came in the front end of the line, but dimensions, level of integration, wafer thickness, we are coming towards the completion of IC fabrication in the back end of the line. So that is why B, C, and D are important for packaging. So in that case, so first we are discussing dimension. It refers to how many leads there are and how close they are. Depending upon the size of the chip, we will have to assign the number of leads that comes on the particular package and how close these chips should be aligned with respect to each other. And then comes integration level. There are actually, when we are doing a package, there is a chip on sorry, there's a chip on system or chip on package. Chip on system means that in that particular chip there will be multiple components, each of these components having a specific function, and they will be in a single chip. If it is chip on a package means multiple chips will be there with different functions and they will be put into a particular package. And then comes wafer thickness. Wafers will usually be thinned down for easy packaging. So once everything has been finalized, excess material will be removed so that it fits perfectly into the package. Then physical vulnerability. We mean that physical. So whenever we are doing an IC manufacturing process in a clean room, a lot of handling will be involved. We will need to move the chip from one place to another. During scribing, care should be taken that it doesn't break or that just wouldn't chip, etc. Therefore, the physical conditions that are encountered by the chip inside the system, like stresses, strains, vibration, etc., gives the physical vulnerability of the chip, and this also affects packaging. And final one is heat generation and heat sensitivity, and an adequate permission must be given for heat dissipation. So we are performing these operations on a very small material, that is in nanometer dimension. Therefore it is necessary that efficient heat dissipation should be given, otherwise the material will heat up and its functionality will be lost. So these are the factors which actually affect the packaging. So is that clear for all of you? Yeah. Yeah. So then we'll move on. On a silicon wafer with 2000 chips and 100 randomly distributed defects, what is the probability of a chip having two defects? Use Poisson's model and choose the nearest value. So first you will have to memorize the Poisson's equation. That is, there will be an equation, right, for finding the probability for a given number of defects. And in this question, you have k values given to you, capital N value is given to you, small n value is given to you. Now, what you have to do is you have to identify the equation and then start solving. So, does anybody remember what the equation was? Just a hint, like something like P of k is equal to, yeah, yeah. Yeah, it's actually m raised to k by k factorial, but the equation is correct. That was a very good attempt. So thank you. And so now I'll project the answer. So see, here it is given that on a silicon wafer with 2000 chips and 100 randomly distributed defects. So N dies. So chip means die, right? So capital N value is 2000 and small n is the defects. N is 100. So capital N and small n are given. So we can find out the value of M. It is 100 divided by 2000, 0.005. For Poisson's distribution, as he already mentioned, P of k is equal to e raised to minus m power k by k factorial. K is already given to you. K value is what is the probability of a chip having two defects. So 2 will be the k value. And when we are substituting all of these values in our equation, finally we will get P of 2 is equal to e power minus 0.05 into 0.05 power 2 divided by 2 factorial. And our final answer will be approximately 1.19 into 10 power minus 3. Is that clear for all of you? Yeah, so everybody, please keep in your mind the important distributions that are discussed during the lectures as well as the required equations for them. They will mention in the question which model to use, but they won't give the equation in most cases. So it is better that you keep an idea when what the equation will be for each of these distribution, and also just don't memorize this part only. We also need to know what is M and what is capital and what is small n. So whenever you are memorizing an equation, please do keep in mind to know what these abbreviations are also. So I hope this is clear for all of you. Does anybody have any doubts related to this? Okay, so I hope that's clear. Now we'll move on to the next question. The process water used in clean rooms during IC fabrication should have low resistivity, high resistivity, dissolved minerals, or photoresist. The process water, like laboratory, in laboratories we usually use some special kind of water. So what is their peculiarity? Does they have dissolved minerals, they have high resistivity, or do they have low resistivity? What would be the answer? Sorry? No, that's not the answer. No. B, yeah. So, clear, like, see, in the the correct answer is option B, high resistivity. In a wafer fabrication, like I already mentioned, see, we had one question where we discussed about the metals that are present in chemicals, right? So, we are actually dealing with very small materials that have dopants in them present in very small quantities. And very much care should be taken that no processes or properties will change the mobility or electrical conductivity of our particular wafer or chip or whatever it is. Whenever we are using water, suppose it has high resistivity or dissolved minerals, this conductivity will be altered or it can be increased, and this will destroy the functionality of our chip. So the chemicals we are using or the water we are using, it should be important that there should not be any dissolved minerals, there should not be any metal ions present, etc. So it should be high resistivity. That is, this particular water that we are using should not conduct electricity. That is why we used deionized water in our laboratory scale experiments, so that whatever property we are intending for does not get destroyed. So, the process water that is used in clean rooms is called deionized water. Normal water contains dissolved minerals, particulates, organics, and dissolved gases, etc., that make it unsuitable for use in fabrications. Dissolved minerals. Is somebody giving a message? I would like to ask them to speak up because I'll have to go back and then read out what they have mentioned. So it would be better if you could speak up. So dissolved minerals they are electrically active and they can destroy the wafer's functionality, whereas particulates and organics can increase contamination. These chemicals must be removed from water before it can be used in fabrication. So is that clear for all of you? Why we use deionized water? So in case of deionized water, it has a resistivity of 18 million ohms centimeter, which implies dissolved ions have concentration of less than 0.03 parts per million. Regular tap water, on the other hand, has a resistivity of 0.004, which it has very low resistivity. It will allow current to pass through it decently, and impurity concentration is nearly 3 orders of magnitude. And whenever we are doing a fabrication under very high purity, it is necessary that we use deionized water, and it should have very high resistivity. So let me check what somebody gave. Okay, nobody posted any message. Then, okay, is it clear to all of you why we use deionized water? Yeah, yeah. Okay, so we'll move on to the final question. IBM is an example of an IDM. IBM is a company, you know, right? IBM. So it's an example of IDM. What does IDM stands for? Integrated Device Microchip Machines Maker or Device Manufacturer. Yeah. So it is an integrated device manufacturer. Can anybody explain what is meant by an integrated device manufacturer? Okay, I think maybe, yeah, please. Yes, that is the correct option. Like IBM, what they do is that they will design their own circuit. That is, they will design the mask, they will design the photoresist. At the same time, instead of giving this design to another company, they themselves will manufacture the physical product also. That is, they will manufacture the wafer also. That is what is meant by an integrated device manufacturer. Other IDM companies include Intel, Samsung, etc. On the other hand, there are certain other companies that we do fabless semiconductor manufacturing, which means fabless manufacturing means that these people will design the circuit, but they won't process the fabric, like the wafer themselves. They will contract it to another foundries like Taiwan Semiconductor Manufacturing, Global Foundries, etc. So that is what is meant by fabless semiconductor manufacturing. Examples include companies like AMD and Qualcomm. IDM or like IDM companies will do the entire process by themselves, whereas fabless semiconductor manufacturing circuit will be designed by these places, but the actual manufacturing will take place in another foundry or company. So that is the difference between these two. Is this clear for all of you? Whatever we have discussed so far? Yeah, so that is actually all for today's session. So if you have any additional questions, please post it in the discussion forum or email me at santra.pmr5atm@gmail.com. Please go through the videos, and whenever you have doubts, please note them down and mail them to me or post it in the discussion forum. So even though our live session, this will be our last live session, I will always be available on my email, so you can post your questions directly, and please feel free to actively contact on whatever you have doubts regarding all 4 sessions that we have done so far, materials, etc. Yeah. Somebody have, yeah? Yeah, yeah, sure, sure. Okay, suppose that each of these yield stations have the same yield, then you can calculate it as x power n is equal to so and so yield. But if the individual stations have different yield, that would require as that could not be got from a direct equation. That particular equation that we saw here, right? So I'll show you once more. Where was it? Huh. See here, what happened is that we was able to use this equation directly because it is mentioned that all the 8 steps have the same yield. So if you have 100 steps and all of these 100 steps have the same yield, you can directly put x power 100. Then we can find the number of steps, right? But if each of these steps have different yield, then it cannot be found out directly. Yeah. you will have to find out the number of wafers that go in, number of wafers that come out, and the other hand you have to find out the number of dies that go in and number of dies that come out, and so on. So I would like to suggest that in the first video, I think sir is mentioning about a particular table where how he calculates when each of the step have different yields. So I would like you to go through that to find that out. Yeah. Yeah, if you have the same yields for each of the steps, it is possible to calculate, no issues. Yeah, that's all. Yeah, sure. Anybody else? So, yeah. Yeah, that is what is given to us. What that is what is the instruction given to us so far. Only 4 sessions will be there. Since it is a 4 week course, only 4 live sessions will be there. But in case they are keeping an additional session, it will be intimated to you via email. Yeah. And if it is there, it will be on Tuesday next week. But so far, there is no instruction. Yeah. 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 I hope that's all. So, wish you all the very best for your upcoming examinations for fundamentals of electronic device fabrication. Prepare well, do your assignments, submit them on time, and please feel free to contact me in the discussion forum or santra.pmrf@gmail.com. So, thank you so much for bearing with me for the past 4 weeks. Thank you, best wishes, and goodbye to all of you. Thank you so much. Yeah, yeah.